the Auto-Twin dashboard, which we use for automating the process of learning and maintaining digital twins. It supports the steps of loading and transforming the data into a system knowledge graph, discovering a digital model, translating it into discrete event simulation, running the simulation for validation and calibration. The first step is to load the data from the common data space into the system knowledge graph raw record layer. This also imports the domain knowledge, which we provide, for example, in the form of Excel tables that detail here for the Croma process, the stations and the sensors in the process. The dashboard also shows when the records have been imported. We can look at them when we inspect the graph database. Here we see how the raw records from the domain knowledge have been imported. Each green node represents all the information that we've seen in the domain knowledge. A green node coming from an event data source, like the one here on the left, it holds all the information of the individually recorded events. During the import, we also identify what kind of semantic information each record provides, so we can link event data and domain knowledge to each other. Next, we turn the raw records into a knowledge graph through simple transformation rules, like the one here on the right that describes how information from sensor records and station records are turned into sensors and stations and their relations. This is done automatically through transforming the data on the dashboard. When a transformation completed, the dashboard shows that various nodes and relationships related to the Croma process have been created in the graph database. Let's have a look. Here we see the information that has been extracted from the raw records. From the domain knowledge, we've extracted a station and a sensor, for example, and that sensor is always part of a station. From an event record, we extract an event with a timestamp, the kit it is operating on, the operator who has worked with the kit, and it is also linked to the sensor where the event has been recorded. In this way, from the domain knowledge, we reconstruct the structure of the Croma process, where kits arrive from the hospital to be cleaned, washed, inspected and assembled, sterilized, and then stored before they're being sent back to the hospital. Each station has two sensors, one for entering the station and one for exiting the station. If we look at how the events of a single kit, for example, are recorded along this domain knowledge, we observe that for some sensors, we have no recording event, for example, when a kit enters the cleaning station. This data quality problem we are solving through inference in the knowledge graph. We address these data quality problems by aligning the records of a single kit along the structure of the domain knowledge of the Croma process. In this way, we are able to reconstruct all the missing events and nicely see how now the process flows along the circular structure of the Croma process, entering from the hospital to cleaning, loading into trolleys, washing, releasing from the washing machine, being assembled, being composed back together, being placed into the sterilizer, entering storage, leaving storage to be commissioned to the hospital. What we also see here is that the same kit at a later point returns from the hospital back into the Croma process for a new round of sterilization. So here we clearly see the circularity that is being present in the Croma process. We use this observation of the circularity to identify the specific individual runs that are being executed in the process. This way, we're able to distinguish, on one hand, individual executions of the process, at the same time track the circularity of an individual kit, which here undergoes further iterations of the process. The knowledge graph allows us to study even further also how, within the process, a single kit is preceded and succeeded by other kits along the stations. For example, this allows us to observe for the kit that we've just been seeing in the circular chain that is being preceded and succeeded by many other kits. And most importantly, we can see that in the beginning of the process, the kits are handled in a FIFO fashion. So kits that are entering dirty material input first are also handled in a subsequent steps first. However, later on, kits are also overtaking. So this kit here is prioritized over other kits. So the rule of FIFO processing is violated. This ordering of kits matters for optimization. All the steps that I have shown are executed automatically through loading and transforming the data in the orchestrator, and the system knowledge graph is ready for discovery.